today I would like to share a case study of stone surge in the Gulf of Thailand induced by the 2019 tropical storm Pabuk. And maybe it's Pabuk. So I'm from Kyoto University now. And in this research, we have several organizations that are participate in these studies, including the National Central University in Taiwan, and the Great Computing Center in Seneca, Taiwan, and HII from Thailand, and also Research Center for Environment and the National University of Singapore. So we also thank these organizations that support this study and make us move forward. Yeah. So in the very beginning, I would like to share with you about a photo that is the Kansai International Airport. And this is very famous in the stone surge research community, that because we know this airport got flooded because of the Typhoon JB. And we probably know that the Japanese research communities has developed for coastal engineering and ocean engineering for several decades, but they still get a stone surge flooding now. So it means that we probably don't understand very clearly about the mechanism of the stone surge. So there is another photo is in the United States. So it's the Hurricane Cindy in 2012. Okay. Wait. Sorry. Yeah. So also the local communities, including the infrastructures, are flooded because of the hurricane. So it means that until now, we still face a lot of challenges from hurricane, typhoons, and stone surge, especially the floodings to this community. So basically, what is the stone surge? The stone surge is an abnormal water level rise induced by the tropical cyclones, storms, typhoons, and hurricanes in different countries and areas that have different names to describe that. So some factors that can contribute to stone surge, like the surface pressure, winds, waves, tides, and bathymetries, all of these factors can intensify the surge height to very dramatic water levels. So you can think about there's a scenario if a stone surge happened and high tide, and above this surge and tide, we still have the waves. So this wave, if these waves hit the coastal infrastructures, that it will cause a dramatic damages. So that's why we need to think about the stone surges issue. And then for the disaster mitigation of the stone surge issue, then comes from different science and the points of view. So in our part, because we are scientists, so we consider more about the earth science part, such as the mechanism of the typhoon, or how can we simulate stone surge more accurately, and how can we calculate inundation and some interactions among tides, stone surges, and waves, and how can we solve the phase of individual waves, and do we have some other mechanisms that we cannot understand? So that is what our scientists, we are doing. And also when we try to focus on like a predictions or the forecasting, we need help from the computer science. So I think the APAN, especially this working group, can contribute the computer science part to the earth science part. I think it's a very good collaboration. But besides of these two, then for the disaster mitigation, then we need the help from the government and organizations, because they are policymakers, or they are make the guideline or the manual to prevent these hazards. So from these three parts, if we can have more case studies to do to understand more mechanisms, so it will be good, for the future. So first, although we are focusing on some case studies, and yeah, we are happy to have more data to deeply understand the mechanism behind the stone surge. Yeah, now we go back to the Thailand, and in this area, and they are potentially there is a flooded prone regions because of the low-lying areas. So if we see this area, they have a very shallow waters and very long coastlines. So they are potentially be flooded by the tropical cyclones or tropical storms. Then if we see the environment around this area, then the countries like Cambodia, Thailand, Malaysia, and Singapore, so these are very shallow waters. And so to say to these water depths, they are lower than 1,000 meters. So if we see the land scale of this, so for the Gulf of Thailand, then it's about 1,000 kilometers. So the open of this is 400 kilometers. And when the tropical cyclone it enters this Gulf of Thailand, then because of Gulf of Thailand is an enclosed Gulf, so something will happen inside this Gulf. And that's why we want to understand some mechanisms in this area. And the mean water depth of this Gulf of Thailand is about 60 meters, so which we can say that it's not very shallow water. It's not very low, deep water, it's a shallow water. Yeah, so the case study we are focused now is the tropical storm Pebble in Thailand. Then Pebble killed about 10 people and caused economic loss for about almost 200 millions. Yeah, so it brought to Thailand about the heavy rainfall and the flooding. Also have some damages lost in Vietnam and Malaysia. So there is from some news they were describing about the damage from the Pebble. So a lot of people they are waiting to take the airport to somewhere they have no rates because of the Pebble, and also the waves hit this port and harbor, and also because you see there is a rainfall, they hit some areas. So this photo saying that Pebble has a strong winds, so they will damage the trees. So you can see the car is driving across this road, and they need to prevent to be hit by these trees. And also the house destroyed, and we have seen flooding because of this Pebble. So several wooden houses they were destroyed during this event. And also these floodings after several weeks, I think they still have the flood depths accumulated in these areas. Yeah, so for the intensity of this typhoon, then the intensity is about this. And sorry, I need to check. Sorry, let me check something. Okay, yeah. So for the intensity of this Pebble, that the pressure is not very low, is almost 1,000 hectopascal, and the wind speed is just 45 knots, and the stone track passed over the southern part of Thailand and make landfall at this time. So that is the wind fields of this event. So you can see the Typhoon Pebble going into the Gulf of Thailand and make landfall at south part of Thailand, and then pass over it to the Andaman Sea. Andaman Sea. So the scale of this typhoon, roughly speaking, is 200 kilometers of this. So the length of Gulf of Mexico is twice the typhoon size. Then when you make landfall, then you could see the uh, cyclonic winds hit the coast, and another side will hit also cyclonic waves hit another side. And then now we have the two gauge data to validate our results and see what is the water level rise and the storm surges near the coast. So and also we think this data set they are delivered by Verchai. So from the gauge observation with tide signals, then for the co-Simon and the co-prop, then I will call it KAs and KP stations. Yeah, so at these stations, we know that the typhoon landfall, at least tide moment, and we will see that. So the maximum storm surge will happen. So near the low tide moment. And if we minimize the tide effect, just focus on the storm surge alone, so you could see there is a D-tide signals. So the storm surge goes down and then goes up again, and they go down. So the duration of the storm surge at the KA stations is about 2 days. Yeah, so also at KP stations, we can find that there is relatively significant signals to the KA stations. They goes up and then increase gradually and then go down. So the maximum surge is about 0.5 meters at KA stations, and another storm surge height is about 0.7 meters at KP stations. So we can use these two data to validate our storm surge simulation. And now the model we are using is the Concord storage model. So this model solves the depth integrated range equation models with the sea level pressure gradient and wind shear chest, bottom friction, and horizontal eddy dissipation terms, with the gray nesting function and the shoreline chasing method to calculate inundation and try to use some appropriate grid size and the domain to calculate storm surge from the ocean to coast. Then we also adopt the OpenMP parallel computing with nested grids that it can back our efficiencies more than 10 times than the original stereo versions. And this algorithm has been adopted to the storm surge calculation. And is originally from our Concord tsunami models, or just move this algorithm to the storm surge version. Yeah. So after developing this model and try to make it run faster, then we need to validate our model to prove that its accuracy is enough to solve the practical problems. So the first one, model validation, is the soliton-like waves, then which is the transient signal propagate from on the constant water depths. So that is the wave shape in the space and time domains. Then in the right side, there is the animation. So trying to, we have a soliton-like wave propagate from left to right and with a different green size. And you could see everything. Yeah, they just stand from left boundary and propagate to the right boundary. And so you can see some difference in between that. The blue lines are our simulations and the dashed lines are the analytical solutions. So if we choose the grid size and if they are coarse, for example, like this and that, then we will have some lag or shift. But if we choose grid size to some certain levels, they are fine enough to solve this wave problem, then we will not see this. But we still have some difference in shape. That is because the analytical solution are from some higher order theory. So in our shallow water equations, that we try to focus on the peak value and the arrival times of the wave shape, not try to make all agreement to the whole shape. Yeah, there is some frictions from the right boundary, and then if we choose the fine enough grid size, that the reflection sometimes we said that we can ignore because we cannot always find enough boundary conditions to describe these transient signals because it's very hard to deal with this problem for open boundaries. Yeah, so another numerical experiments is for nested grids. We try to choose some different grid size to do the validation. So you can see the all waves pass over the nested grid successfully and smoothly without any artificial reflections generated. Yeah, another thing is that we try to use some oblique incident waves from the corner to another corner. So that is from different angles for 40 and 45-degree angles and 60-degree angles. So based on these two, then we expect to see two patterns. One is the symmetric wave patterns, another is non-symmetric. So these two different angles can use to convince our model deal with the nested grid for these four boundaries. So the larger one is the coarse grid, and in the center, which is the finer grid, try to use to solve the wave problem. Then there is a 45-degree wave incidence. Then you could see the waves propagate from the boundary to the central areas. Looks like that. So it smoothly pass over the focus area. So for another angle, you can see, yeah, there is also no reflections. So based on that, we can convince everyone that, okay, so the nested grid functions is fine enough to deal with the wave problems. Then another one is the run-up problem. And this run-up problems is related to the flood depth calculation and inundation calculation. So that's why we want to validate. And this problem is a benchmark problem of NOAA. So there is a conic island in the center of that. So there is a solitary wave sent from a boundary to hit this island and to see the wave pattern around the island and also the run-up height. So there is the computational domain, so I probably will ignore this part. And then there is the elevation C. So the incident waves are from up and propagate along the boundary of the island. So you could see the wave run up just behind the island of that. So there is a significant run up and inundation. Okay, just repeat it again. Yeah. So if we use this data to validate our model with the laboratory experiments, so you could see, and the red lines are our simulations. So the black dot are the experimental data. So in the arrival time and the peak value of that, so they match each other, yeah, reasonably. So so it validates our model. And another thing is for the inundation depths and areas. So if we make the data projected to the island, then use our model to validate, and also it match well with this run-up height onto the island. Yeah, so besides the validations from the experiments and analytical solutions, we also try to use our model to validate with a real typhoon case that which is the super typhoon Haiyan. Oh, sorry, I ran out of time, so I will say more quickly. And the Haiyan in the Asia is quite a famous case because with the strong winds and very low pressures, it caused a dramatic water level rise to coastal regions. And then our study area is focused on the Leyte Gulf and especially in the San Pedro Bay, because the winds hit this area, and from the field surveyed, there is a severe flood depth and very large stone surge heights were found here. Yeah, so we used the nest degrees for 3 layers to simulate the Haiyan case from ocean to coast, and especially focus on this area is called Tacloban. And because of the Tacloban, as my understanding, there is the airport, and because of the stone surge of Haiyan, and these airports got flooded. So we focus on this small area. So from the big to small, to also convince our simulations can from large scale to small scale. Then we use the parametric wind model to reproduce the winds of Haiyan. So this is the parametric wind model they were produced by the Hollands. So you could see there's a best track, then is the Typhoon Haiyan. So with very strong winds, they go along this, and then the winds hit the coastlines, and then it changes its wind direction to more north. Then because the wind, they push the water to the bay, so we can expect that there will have a severe stone surge around this area. And also that is true that from our simulations, we see the severe stone surges, all of these are focused on this bay. So for the Paddle, Tanuan, and Tacloban and bases, they have a stone surge smaller than 3 meters. And if we correspond to the wind directions, that also we push the stone surge to the bay. Yeah. So there is the inundation simulations from our models. So there is the location of the Tacloban airport, and this airport is flooded because of a stone surge. And also we can see the way the flow direction is changed. So before the landfall to after the landfall, so there is a anti-clockwise vortex generated in this Battle Bay. So from the stone surge signals, if we see at the Tacloban stations, then the signals goes down and then goes up dramatically within 6 hours. So in some papers, it describes that the water levels drop first and then increase very quick. Then sometimes they say it's tsunami-like stone surge. That is because of this pattern. So let's go back to the tropical stone pebble case. So also similarly, we use the nest degree to simulate this typhoon case. So from large scale to the smaller scale. And now, because we are doing this case, so the grid size in the first layer is 4 kilometers, and the second layer is 1 kilometer. And so in the left part is our computed stone surges. In the right part is the wind. So when the pebble is just off the coast because of the wind, and you can see the stone surge generate to the wave patterns, to the wind patterns. So when the stone center is approaching the coastline, then the wind hit the coast. So you will see in this part, we will have relatively severe stone surges. Then when it makes landfall, the wind direction changes. But surprisingly, we found that to the north part, in this area, there is a higher stone surge they will generate because of the winds. But for the near the location, near the landfall location of the typhoon, that the stone surges also cannot be ignored. But relatively, the north part has larger stone surges. And also, these patterns, so the winds push the water to this area and make larger stone surges than other places. So also like that, we also see the dramatic stone surge. And so after it make landfall to the Andaman Sea, then we also see these patterns, but the surge move to more north part. And then he is near the end of the story. So if we use our simulation data to compare with the gauge observation, that we can find at KA station and KP stations, our simulations agree well with the observation. So for the peak value and the arrival times, so it makes that our simulation can capture the stone surge from ocean to coast. So another thing is that we also we also be curious about is the wind dominate or the pressure dominate the stone surge generation in this case. So because of we are using a numerical model, so it's easy to understand each physical factors. Then we separate these two factors and then run the simulation. So we found this case is the wind dominate case. So you could see the wind driven surges, I will call it, is 220 times or 30 times than the pressure driven surges. And we can see the pressure gradient here in this case that it can be ignored. So only the wind is a dominant one. And now, so for the summary and the next step for this case, now Kanka can simulate the stone surges by this event in the Gulf of Thailand. So then we use the EIFI data as the input to drive our model simulations. Then the comparison at these two stations, KP and KAs, are matched well. Then we found the wind shear stress is a dominant force in turn in this case. So for the next step, we are looking for more data to validate these type of models, such as the inundation and more detailed bathymetry to do the flood depths. And I think it's a very good case studies for Thailand and also for the Asia countries to understand that even the storm intensity is not very severe or not very strong, it can also cause some damage and the disasters to the coastal areas. And we plan to write a manuscript to submit to journal. So in this year, and I hope that these case studies can pave the way for the future stone surge studies and in the Asia research communities and also in this working group. So I probably will stop here, and thanks for your listening and welcome questions and comments. Thanks.
Thank you, Dr. Tsai, for your excellent case studies. Thank you, Dr. Tsai. This is Franz. My question is, would your model take into account the rising sea levels? How does the model develop the rising sea levels?
Oh, sorry, because I hear some echoes from the microphone, so I cannot understand. your question. So I'm sorry, I just can't understand the models or something.
Right. Can you hear me better now?
Yes, yeah, okay.
Yeah. I'm just curious. Can your model take into account the rising sea level as well because of course, because of climate change?
Yes, you see the sea level change? Yes, yeah, yeah, we can. If you means considering about the scenarios of the sea level rise and some other things that is able to do that, but because now we are focused on some case studies, but in the futures we want to understand some other factors, yeah, such as the future climate change or sea level rise. So it's fine to do that.
Okay. Thank you.
Yeah, thanks for your comments.
Didn't see any question from online. Thank you, Dr. Tsai.
Okay.
Thank you so much.
Okay, so maybe I stop sharing.
Yes, thank you. And then
Okay.
the
Thanks.
Yeah, it's from Moon about the spatial temporal drought analysis. It's your slide. Share your screen.
Hello, can you hear me? Hello.
Yes, we can hear you. Would you please share your slides?
Yeah. Yeah, thank you. Give me some moments to share my slide. Hello, can you hear me?
Yes, we
Hello.
can hear you.
Can you see my? Hello, my internet
Yes,
connection
we can
have
see
some
your
issue.
slides now.
Can you see my PowerPoint?
Yes.
Yeah, thank you. Thank you. So I'm Muhammad Abdul Al Mamun, right now studying in PhD in Hong Kong Baptist University, Department of Geography. Today, my topic is spatial temporal drought analysis in the coastal zone of Bangladesh. So Bangladesh coastal zone is really famous for agricultural production, but nowadays, due to the global warming and climate change, some drought are seen in various parts of the country. So I organize my presentation through introductions, where I want to share the background of the study, then research gaps and the objectives. So to begin with, droughts are the biggest threat for food sector, actually in food security aspects around the globe. More or less 55 million people are affected by droughts directly or indirectly, according to World Health Organization 2022 data. And it actually threat the agriculture management, especially the food security and sustainable environment. So Bangladesh is also a victim of this drought. So if we see the previous empirical studies, we can see the more than 46 drought events occur from 1951 to 2009 and causes catastrophic impact on Bangladesh food sector. So here I can show a figure that that is given by NOAA and National Oceanographic Atmospheric Administration USA. The darker the color, the number of people, more number of people are affected by flood. But you can see that Bangladesh has a very deeper color. Secondly, we know that the coastal region is famous for agriculture, and that gives the boost of the food production around the country. But due to the climate change and the low water holding capacity that is depicted by many different studies, that the water holding capacity due to the seasonal drought and less or over rainfall, untimed rainfall, create this farmers of agriculture in based the coastal region have to rely on more water ecosystem. So the adjustment actually done in Bangladesh based on northern and northwestern part, that is the north part of Bangladesh, that is known for the dry area, but less concentration given on the southeastern or south northern part, that is mostly famous for agriculture. And the Bangladesh aspects, most of the meteorological and hydrological drought analysis is considered, but less agriculture drought analysis is considered. That is the research gap of my study. So considering this as well, I also see done some to applied to methods to farmers group discussion methods, qualitative study to see what they feel and what their idea about shifting away the pattern. Based on this, the objective of my study is to assess the agriculture drought in southeastern part of Bangladesh, whereas to explore the perspectives of local farmers, those have like 20 to 25 years farming experience regarding crop cultivation and climate change. So my study area is coastal district of Bangladesh, or 19 districts are known as coastal districts. Have well, I will go for all the coastal districts of Bangladesh. The data sources as gridded grace release RL06 MESCON data with a spatial resolution 0.25 to 2.4. 2015 years, because the data has like 15 years time period. So I use the STI, Standardized Terrestrial Water Storage Index, that has newly adopted techniques. And I also take a qualitative approach, like two farmers focus group discussion. And then I transcribe the textual analysis and try to find the relationship between our quantitative results. The first of all, the result is the STI have 1, 3, 6, 9, and 12. That means it is it can be measured by 1 month from like January, February, March, April, and then if I can take 3 months as well, like STI 3 means 3 months. If you start from January, then the data can give the drought data in March, and that's why the STI 6 is 6 months, STI 9 is 9 months. So based on this criteria, we can see that the drought events is 2 to 4 drought events. If we can see the slight yellow to slight red, number of drought events increase. We can see the increase in every area like Chittagong, Feni, Hatia, Maizikot, and Sitakundo, whereas the wet season is also extreme in some point of time. So, and also you can see the 12 like 1 year drought period between 2002 to 2017. We can see like 2 to 3 severe to moderate drought even occurred every year in all the study location. Done for drought, like hydrological drought or meteorological drought in the northern part of Bangladesh, indicating that the previous 15 to 16 years, the drought even is actually increasing. That align our study as well. Though we take another index called STI, Statistical Storage Water Index. And coastal regions are famous for like rabi crops. There are 3 types of crops, rabi and khisti, that is done all around the year. The rabi crops is fully dependent on the weather because it cultivated in mid-March to mid-October, this 6 months. And our agriculture farmers are actually dependent on soil structure and timely precipitation. So if the timely rainfall is not happen, farmers are facing serious challenge to get a good product. Here we take another approach that is called STI minimum values. So the STI values from 1, 6, 9, 12 minimum values, and then plot it in a graph to see the trend by man candle trend test. So all the STI 1 to 12 see the decreasing trend, and all the parameters are statistically significant for the Feni weather station study area. For the other weather station like Chittagong and Maizikot and Hatia and Sitakundo, it can be seen like the trend is decreasing. That means the drought intensity is increasing, but the STI 9, that is from 9-month period, the drought intensity statistically significant. So we can see that though the coastal area is known for its good weather and better agriculture production, but the slower intensity of drought is increasing. That is termed as agriculture drought. So for that, we take the drought as our water deficit consideration, and that means in that time soil water availability are at a risk and soil moisture has reduced, so that our STI captured the occurrence better than SPEI or SPI, that is famously used for drought assessment. So later we take 2 focus group discussions. So we collected farmers' information from Agriculture Department and local Bangladesh Agriculture Extension Office, and we take 2 farmers groups focus group discussion to talk with them like climate change and the traditional agriculture perspective. So focus group 1, many participants mentioned that the heat and drought was not the problem a couple of years ago, but now last 2 or 3 years, change of like lack of rainfall sometimes decrease at faces the dry period compared to previous time. And other focus group also mentioned that they demanded heat tolerant seed and like high temperature seed to maintain their regular food production level, as because the rainwater and the sackback technique cannot be executed because of the untimely rainfall and dry period in that area. So based on that, we can see that different stakeholders' explanation in our drought analysis actually established a slow onset of seasonal drought that actually create some problems for their agriculture production in that coastal region. That also many studies highlighted in many different parts of the world similar coastal region, and that means that a drought are more catastrophic compared to a flood because it is a slow ongoing process, and sometimes policymakers and the administrations overlook these problems. So in conclusion, I want to mention that the agriculture drought events increasing like 2 to 4 events every year, whereas the STI minimum values in these 5 weather stations actually increased. That means the agriculture drought has an impact on this area. And also the local farmers' perception actually agree on this matter, and because they demanded agriculture adaptation techniques, and also they demanded or heat tolerance seeds from the government. So that is now my findings based on the 5 districts. If these findings will submit a paper in the journal, it goes on, then I will go for like 19 districts, more robust and more area based drought assessment. So here is some references for my study, and thank you for listening my presentation. And now I'm open for any questions you have.
Thank you so much. That's excellent.
Hello, can you ask the question again, because I cannot
uh,
hear the question.
right. The drought event that you found happened which month in Bangladesh?
South of Bengal, that is called coastal zone, Bangladesh. Yeah. Hello, I'm sorry for if the internet connection is not good. I cannot hear you.
Oh, okay. One last time. Which month that you found the drought event in Bangladesh?
Yeah, from mid-March to mid-October, because I targeted the Rabi crops, the crops that is suitable for the coastal area, my study area. And the farmers actually taken the 6 months as a Rabi crops, is in local language, but they're farming this crop from mid-March to mid-October. So I counted that 6 months as my drought assessment.
Thank you for your presentation, Mr. Abdullah. I'm Gracia from Indonesia. I'm just wondering if the drought has been fluctuating. You know that as the climate change happened, it might be difficult for you to count how effective this STI value measuring the fluctuating drought. Let's say from May until September, there are only 2 droughts in those months, and then very much rain. So I'm just wondering how this STI value can be more effective when we cannot predict that drought and the dynamics of the drought are unpredictable. Thank you.
Yeah, thank you for an insightful question. Yeah, you are right, because one index is not enough to assess the drought on this area and like 6 months. So yeah, I'm planning to take more indexes like hydrological and meteorological. It's called SPEI or SPI index. And that's why we've taken the focus group discussion of farmers, that the main beneficiaries, how they feel the challenges of their own experiences. So that indicate that the diet period is increasing. Now we have to establish it through quantitative indexes. So that means I have to take more data and more drought indexes, as well as more points on the area that will have the more coverage, and then we can validate our STI index based on more other validation indexes. Thank you.
This is not the question is just a question. Because of the drought and the climate change, I think this is also the locust invasion risk is increased. And this is just a comment. It's about the locust, the invasion may increase the high risk.
Okay, okay. Thank you. Thank you for your nice comments.
Let's think. So according to the program, next will be about the summary and also update. The brands mentioned by the regular brands. It's been organized. Objective of this as you can, as you know, also from the speech is challenges. Sitting is about and also we also need such as years that did several so based on the requirements from the user primary standards what sizes we utilize total loss. Once we understand the root cause of each event, then we can improve the numerical simulation and based on the revised, more accurate numerical simulation that will help the preparation of future events to loss. That's the basic ideas of the deeper understanding approach. So from those case studies, we also develop best practices, risk analysis based on the knowledge. From the case study, we organize all the materials and also tools and also make all the accessible, share to the knowledge. just by develop some simulation such as simulation based on concave model. So there is tools such as WRM as a variable source. So we have different all the partners in this collaboration support the engagement of the local citizens identify from the user and also the services, so that the innovative service can develop and ship. Of course, in the future, that there's different sustainable development requirements from different countries. That could be also study. That's what we like to do in this. So even during the COVID experience, we still hosting the disaster mitigation group meetings and meetings virtually. It's great to back to normal in-person meetings. So in the future, the momentum of the collaboration could be increased a lot because of all the from the working group meetings, we hope have status update from the case study to understand the requirements of the system. And in the we also has a master class of training course and meetings support from desktop or other and some related sources that will be very helpful. This is just a simplified ideas of the deeper understanding approach. So, for example, based on the discussion, we choose the case. One of the case. It's very hard to simulate the strongest wind and also the lowest pressure. Simulation models before, and it caused a lot of losses in Philippines. And then, so the first thing is we need to collect of the big data in the station. Census stations. Then together we have scientists understand the data and by the simulation models. Test simulations. Understand the against. Then iteratively the simulation processes will be improved based on then with the knowledge gained from the analysis that the simulation output that's up to the requirements from the users from the searches of the science by objectives. Another possible outcome from such case study that would be important. That's one thing. I think that make all the materials open. That's why we towards the That's one of the directions. This is the table of the summary of the case studies in the past 5 or 6 years. As you can find, there are different types of cases. Type of service, industrial product, inspire monitoring, and also the simulation photo development, etc. So for different for each taser type, we have leading sciences coordinating the integration efforts. That's needed by about the typhoon and storm surge. Dr. Tsai is one of the leaders in this part. Last transportation that's needed by this front that's now needed by visiting Malaysia. Dr. Vera Chai is leading the monitoring as this. In fact, we also need infrastructure support for the tsunami simulation portal based on icon card that's been online, supported also by the ETI, by the European founded design simulations. So that means to the marketplace, the users around the world to access to this. It's about for now, that's based on first effective use. So you only need to the few parameters of the first effective source. It's process of it based on the once we had a collaboration meeting in Bangladesh, they initiate a new comments from to spend some outline. And as I mentioned, the first thing is to have the observation data in place, which needs support from the it's still in the state. So for each hazard types, you can see different case studies. Most of them about 18 or studies take it out. So next stage is to organize those finish the case study state share. And with the improvement of the IWOS structure, that means knowledgeable parameter applications, achieve more accurate simulation outcomes. And recently, simulations understand the local such century that's also another interesting study. Landslides towards the submarine. Events areas. Interesting. That is the policy. This distribution dust, other areas. Also, they currently know that in last year there is a volcano eruption, which also caused the by this space. Another is about the numerical simulation. At least in Taiwan, we set up high density sensor networks. So we can collect data continuously from hundreds of sensors in this island. So we also build up the sensor network so systemic way application. Right hand side, that's another online check. Updates every 1 or 2 minutes. What's the system way? The other thing that the sensor is also which sensor use objects are one one of the vision from the collaboration that we hope build up smart. So as you can imagine, the virtual simulation and also the deeper understanding approach. In the beginning, I focus on the top and with the support from the satellite image techniques, such as the information. The second thing, and we can provide the information for the response. But we didn't have such case study or such expert group that right group different basis. But the deeper understanding to the science or to the root cause of the risk indicators, and also to support the early work. That's what we are doing several case study has been. The other thing that's about the infrastructure of the satellite, which is based on the open data cable from inside Europe. They've been invest a large money building up such services to those systems, access those free satellite resources such as. So that's we can also leverage such experiences to build up the systems for our needs. In collaboration with those satellite resources. Same thing on each APAN is one of the primary collaboration frameworks and it's the disaster application. We need the user community, we need scientists, we need all the different partners, stakeholders to work together based on the targets. We also working with the leading agencies such as supporting so that data access and also data sharing, web-based services to media access to media shared science. So, through the joint workshop or the working group meetings, I see and that's why the primary IGC one another joint workshop on disaster meetings. That's another chance for us to have interacting with the European team. Observe data, other data partners. The support, funding support from the Asia Connect. We conducted several training events in different countries, even Myanmar, Bangladesh, Malaysia, Thailand. Topic Thailand one is a virtual event. The CREDA project that is integrate the data application with for example by several events also. And we have a new working group, open and sharing data. Have meetings in the afternoon sessions. So, also like to leverage the support the sharing of the all materials. We also like to work in with the agricultural and spread the cases that's introduced by Mendoon to be easier to be shared in the agricultural communities or to try the drought analysis model. That's of course in the future APAN meetings coordinate such together with our studies or because there are a lot of challenges and also very effective is case studies that studies better model to leverage in future of course welcome the scientists in your country in different departments join us through the collaboration with the certification we are now able to access more satellite resources not just for so resources from sound and with those requirements or applications also help to improve the support rapid failure and we need to support share the data and services based on the quite system manual. Considering the privacy of other issues. So we working good from again, one of the primary objectives is without the capacity. So how in the future can venture deal with the changing natures and also the issue whether to support the sustainable development. So this is the program of the joint next. The remote participation is also virtual. We have 6 sessions in 3 days from 3 to 4. That's a in-person meeting organized by topic of the joint meeting is being attended at the risk of energy saving, energy efficiency issues. So the coverage is here is just the 3 sessions mainly contributed by the Japanese. So some and those so have by Professor the big scientist with the related now his research focus to be their part. Another one is when you talk to somebody, it's the expert sounds of the next week. That's the part of the basis. So we are very lucky and we have many precious contributions from all the partners. So, thanks. So that's the update. No question to the operator. Yes.
Thank you so much for sharing all the details of this working group. It's very interesting to see the progress and the update. I'm just wondering if this APAN disaster mitigation has been connected to UNDRR, the disaster risk reductions under the United Nations, because last year, Indonesia was the host of that big meetings, included around I think 5,000 participants in Bali. And there's also a specific stakeholder engagement meeting every year. If this working group is happy to be connected there, I can help to support that because I've been involved for around 2 years now, and it's pretty open so that and that engagement group is flexible, and we also have like a regular meeting online. It's just like another source of networking. If it's another new access to work together in this meeting group. Thank you.
Thank you so much. That's very, very useful.
One for that is for forest fire. We connected to the global fire, wildland fire research. You will see in the next session.
Yes, thank you so much. Before today, last time in the future very happy. I think it's time to have break first. So we'll come back again. We have another session by so very sharp. Thank you so much. Respect at 11.